Hello everyone. In this lesson we are going to look at how we can learn constraints from data, and specifically from process data where the system might be behaving well under certain conditions and failing under others. The idea is we only have input output records, but we don't know the actual constraints of the system. Can we figure them out just by looking at patterns in the outcomes? That's basically what constraint learning is. And we will be building a small but complete setup to test that out. So let's start with the data generate function here. By the way, you can see libraries, and let's scroll. This function here is called generate synthetic data, and all it's doing is creating a simulated dataset that mimics some kind of manufacturing process. We have got two key variables in this process: temperature measured in Celsius and pressure in megapascals. Now let's look. Even though the function looks like it is generating data randomly, there are actually some hidden rules behind these scenes. These are the constraints we will eventually try to learn. They are listed in the doc string at the top. The temperature needs to be between 150 and 350. The pressure should be between 2 and 8, and there is a third one, a nonlinear constraint. Okay, and basically the pressure also has to stay below a curved boundary that depends on the temperature. It's defined by this expression: pressure has to be less than or equal to negative 0.0 times squared plus 8, and that's okay. So what this means is the process has a safe operating region, and only if all three of these conditions are met, the output will be good. If not, the process fails or gives bad yield. And now let's look at how the data is generated. First, we create two arrays, and what are they? One for temperature and one for pressure, and each one is filled with random values, and they are sampled from a pretty wide range. Temperature goes from 50 and to 450, and pressure goes from 0 to 10. And okay, I think, and so this includes both valid and invalid settings on purpose. Then there's a base yield value set at 85, and what is that? That's the baseline for when things are going well, and right after that we initialize an array called what's that, product yield with zeros. That's important, you can see, and that's okay. And after that this is where we will store the simulated quality metric for each sample. And okay, now go through each point. So every temperature pressure pair we check whether it satisfies the three constraints. The first two are just simple bounds: is the temperature in the right range, and is the pressure in the right range. The third one checks the nonlinear condition. So is the pressure below that curved limit we mentioned earlier? If a point passes all three checks, it gets assigned a high yield, but it is not always exactly the same. There is a bit of variation depending on how far the point is from the optimal setting, which is defined as 250 Celsius and 6 MPa. So the closer a point is to that optimal spot, the higher the yield will be, with some randomness added on top. That's done by calculating the distance from the optimal point and scaling the yield based on that. Okay, on the other hand, if the point doesn't satisfy the constraints, meaning it's outside the valued region, it gets assigned a much lower yield, again with a bit of noise. And just to keep things realistic, we make sure the yield doesn't drop below 0. And finally, you will see all of these combined into a pandas data frame with 3 columns: temperature, pressure, and yield. And that's the dataset we will use to try and recover the constraints later on, just by looking at which points performed well and which ones didn't. Okay, I think we can continue. Here, let's look at how we are going to learn the constraints from it. And we have got this class called Constraint Learner. This is basically where all the logic sits for identifying feasible regions and learning constraints from the data. The constructor takes 3 arguments: the data itself, the name of the target column, which in our case is going to be yield, and a threshold value that defines what we consider a good outcome. So anything with a yield above that threshold will be treated as a successful operation. I think it's okay. And inside the class, we just store those values: the data, the target column, and the threshold, and we initialize an empty dictionary to hold the constraints once we learn them. You can see here. Okay. Now the first thing this class can do is identify the feasible region, and that's done in the identify feasible region method. So let's walk through this part. What we are trying to do here is isolate the subset of points where the process performed well, meaning points where the yield is above the threshold we defined earlier. And we start by filtering the data, and that gives us good data. You can see here. If none of the data points meet the threshold, we just exit early, and there is nothing to learn from in that case. Okay, and next we extract the input features so that everything except the target column. These are the columns we will use to figure out the shape of the feasible region. Okay, and now before we run any clustering, we standardize the input values. You can see here. And this step ensures that both temperature and pressure are on similar scales, so one doesn't dominate the other during distance calculations. We use standard scaler for that. That's okay. And once we have scaled the inputs, we apply a dbScan. dbScan is a density-based clustering algorithm, and it is useful here because we don't want to assume any particular shape for the valued region. We just want to group together dense areas of successful data. After clustering, we check if there is more than one cluster. If there is, we keep only the largest one. The idea here is that the main cluster likely represents the valid operating zone, and smaller clusters might just be noise or outliers. If there was only one cluster or everything was grouped together, we keep all the good data. Either way, this method returns a data frame of feasible points, meaning high yield data that we think belongs to the valued region. Now, once we have got those feasible points, we move on to the next step, which is learning some simple constraints. And let's look. So let's scroll down and look at the learn simple constraints method. This function takes in the feasible points we just got, and for each feature, like temperature and pressure, it tries to estimate a reasonable mean and max value. You can see. That's okay. And first, it keeps the target column. We only care about the input features here. Then for each feature, it calculates the minimum and maximum observed value from the feasible data. But we don't want to overfit to the edge of the data, so we add a small margin, 5% of the range, just to give it some buffer. And that way, we are not learning constraints that are too tight or based on outliers. We also make sure these adjusted mean and max values stay within the bounds of the overall dataset, just as a safety check. That's okay, I think. And what can I say here? Finally, we run to values and store them in self constraints dictionary, and each entry in the dictionary holds the mean and max range for one parameter, and then we just print out what we have learned. And I think that's okay, and we can continue. Let's scroll. Now, once we have learned this basic constraints, just simple min max range, it's helpful to actually visualize what those constraints look like on the data. That's what this method does here. It's called visualize constraints, and it lets us pick any two features, say temperature and pressure, and see how the constraints apply in that two-dimensional space. Now, before anything else, the function checks whether we actually learned any constraints. If not, there is nothing to show, so it just exists only with a message. And assuming we do have some constraints, we set up a plot using matplotlib. This is a scatter plot of all the data points colored by the yield value. So the higher the yield, the brighter the color, and we are using the Viridis color map to show that. And I think that's okay. Everything is done here, and that's okay. And the color bar on the side tells us what the color scale represents, which is yield. And next, we draw the constraint boundaries for each of the selected features. And if feature X is in the constraints, we draw a red dashed line at its minimum and maximum values. Same thing for feature Y. These vertical and horizontal lines help show the bugs that the model has learned as the valued region for those two parameters. After that, just to give the viewer of reference point, we draw a light gray axis line at 0 on both the X and Y axis, even though in our case the values probably don't go near 0, but it's a useful guide. That's okay, I think. And then we label the axis with feature names, and the title tells us which features we are looking at. So it will say something like learn constraints for temperature vs pressure. That's okay, and that's done. Now the important part is here. The block draws a rectangle to highlight the actual feasible region. This is just a visual aid showing the box bounded by the min and max values of both features. If we have learned both temperature and pressure constraints, we can build that box. We do that using a PLT rectangle. Here you can see, and it's drawn in red, not filled, with a label, so it shows up in the legend. It gives a quick visual summary of where the model thinks the high performing region is based on those simple constraints. And finally, we add the legend, adjust the layout so everything fits nicely, and displays the plots. Okay, we can continue. Here we will move on to learning a more complex constraints, one that's not just a straight min or max, but a curved boundary between temperature and pressure. This method is called learn advanced constraints, and it's meant to show how we can use a simple machine learning technique to learn a nonlinear relationship from the feasible data we already identified. So first, it checks whether we even have any feasible points to work with. If not, it exits only. Then we get the feature columns. Again, everything except the targets. And what we are doing next is only relevant if both temperature and pressure are in the dataset. If they are, we go ahead and extract the values for those two features. Now, just for demonstration, we fit a quadratic curve. We are not trying to be fancy here. We are just saying, can we describe pressure as a function of temperature using a second degree polynomial? Okay, I think it's okay. It is done, and what can I say here? We use MP polyfit to do that. It is a curve of the form, what is that? A multiplies temperature squared plus B multiply temperature plus C. And once we have the coefficients, we store them inside the constraints dictionary under the nonlinear. We also store which features the constraint applies to, in this case, temperature and pressure, along with the type of model, which is just a string saying it's quadratic. And that's okay. After that, we print out the actual formula. It learned something like pressure is approximately a times temperature squared plus B times temperature plus C, and it is just a way to check that the fit looks reasonable. Okay, and then we move on to the visualization. You can see here we create another scatter plot of all the data points, again colored by yield. Same idea as before, we try to show where high and low performance happens. Then we set up an X range that goes from the minimum to the maximum low temperature constraint. For each X in that range, we compute the predicted pressure using the long quadratic model. And we plot that curve on top of the data using a red line to show the boundary. That's okay, and below that we also redraw the simple min and max constraints, so the vertical and horizontal lines we saw earlier, just for context. Finally, we labeled axis and the title the plot. This gives us a pretty good visual summary of what the model thinks is the nonlinear boundary between valid and invalid regions in terms of temperature and pressure. Okay, so once we have learned the constraints, both the basic min max ones and optionally a nonlinear one, the final step is to use them to recommend the best input settings. That's what this last method does, recommend optimal parameters. First, it checks if we got any constraints learned at all. If we don't, there is no point going forward. Then we filter the dataset to only include the points that had a yield above the threshold, so good performing runs. From there, we go one step further and filter those points again, this time making sure they fall within the ranges defined by the learned constraints. It skips the nonlinear one here because it's just focusing on the simple bounds. So the idea is, from all the data, keep only the points that both performed well and stayed inside the feasible zone. Now, if there is nothing left after that filtering step, meaning no point met all the constraints and had high yield, it just exits. But if we do have valid candidates, we look for one with the highest yield among them. Okay, I hope that's okay. And the best point is returned, and the method also prints out its parameters. So we get the recommended values for each input and the expected yield for that configuration based on the data. And so that's the full learning and recommendation cycle. And down here in the main block, everything we have written is tied together. We start by setting a random seed so the results are reproducible. Then we call generate synthetic data function with 2000 samples just to have a large enough data set. And we print a quick summary of the data. Then we initialize the constraint learner with a yield threshold of 85. What is that? That means we will treat any run with a yield above 85 as successful. Then we identify the feasible region using the classic method, learn simple min max constraints, and visualize those constraints in the temperature pressure space. After that, we also fit a quadratic curve to estimate a nonlinear constraint between temperature and pressure. That part's optional, but it adds more detail. And finally, we ask the system to recommend the best parameters it found, so the best performing setting that still satisfies all the learned constraints. And okay, after running the full pipeline, here's what we get. This part at the top is the summary of the dataset we generated. There are 2000 samples and we have got 3 columns. You can see temperature, pressure and yield. The temperature values range from around 51 to 450. Pressure goes from basically 0 up to almost 10, and the yield ranges from 0 to about 101. We can also see the average values, so the mean temperature is close to 250, which is right around the center of the valid range we defined when generating the data. Same goes for pressure, the mean is just under 5. Then down here we set that the model identified 59 points as part of the feasible region. These are the high yield runs that DBScan grouped into the largest cluster. And based on that, it learned simple constraints for temperature and pressure. The temperature should stay between 236.1 and 266.33, and pressure should stay between 1.77 and 8.21. So it narrowed down the space quite a bit. It's a small band around the optimal area. And here, okay, you can see. Look, okay, let's look at the plot. This is showing all the data points from the dataset, and each dot represents a temperature-pressure combination. The color of each dot reflects the yield. Brighter colors mean higher yield, darker ones are lower. And the red box in the center is a feasible region the model learned. That's based on simple mean and max constraints we just saw. And inside that box, you can clearly see there is a cluster of bright yellow points, meaning that's where the process is giving us high yield. And the dashed red lines show the constraint boundaries for each variable, so both vertical and horizontal limits. They match the mean and max values we printed earlier. And at the very bottom we got the nonlinear constraint that was learned using a quadratic fit. You can see the model figured out that pressure is roughly equal to minus 0.0114 times temperature squared plus 5.7 times temperature minus here 708. So that curve runs roughly through the high performing region and gives us a smoother boundary than the box constraints. Okay, and other plot is here. This plot shows all the data points from the simulation. Again, temperature on the x-axis, pressure on the y-axis, and color of each point representing the yields, and higher yield points are in yellow and lower ones fade into purple. So the dashed red lines show the mean and max constraints for both temperature and pressure. So you can see that the model has narrowed the space down to a slim vertical band for temperature and a broader range for pressure. But what's new in this version is the red curve in the middle. That's the nonlinear constraint we learned using a quadratic fit. It's drawn on top of the scatter plot, and it captures the shape of the pressure limit as a function of temperature. Basically, it says as temperature increases or decreases away from the center, the allowable pressure range shrinks, which matches the behavior we built into the data earlier. You can also see that the yellow cluster, the high yield region, falls mostly underneath this curve and within the box. So visually, this block confirms that our constraint learning approach is capturing the right structure in the data. Now, down here at the bottom, we have the model's final recommendation. And let me zoom again. Okay. So it looked through all the high-performing points that also satisfied the learning constraints and picked the one with the highest yield. According to the output, the best parameters are a temperature of 249 degrees and pressure of 6.6 megapascals. The expected yield at that setting is about 101, which is right near the top of the yield scale in this dataset.